Welcome to the 70th Annual Minnesota Concrete Conference promo video. This video highlights how our concrete conference has been a part of the advancement of concrete knowledge. This 70th conference will be unique in that it will be virtual. The Planning Committee is aware of the saturation of virtual conferences and webinars that are available right now. We hope that after viewing this video, you will make the choice to participate in the 70th Annual Conference. We have divided the video into chapters, realizing that not all of the material may be of interest to you. Please enjoy. The timeline on this slide shows important topics and advancements in concrete over the past 70 years. These topics were therefore emphasized at previous concrete conferences. The names shown are the people who will guide us through this timeline. Concrete is one of the few construction materials truly created during the building process. Other construction materials, such as a steel or wood beam, only need a delivery distribution path, whereas concrete requires an additional distribution path of knowledge. The University of Minnesota Concrete Conference is part of that knowledge distribution path. What do you get from attending this year's conference? 0.65 continuing education units for 6.5 hours of participation. Presentations ranging from alternative supplementary cementitious materials to highlighting the new 11 on the River high-rise in Minneapolis. Continual participation in one of the nation's leading conferences for the exchange of current concrete knowledge. The conference will offer you a lot, but the Planning Committee would like to give you something right now. The Universal Concrete Mix Design, which has been used throughout the world for centuries.
3部分摇滚2部分沙1份水泥1半的水
3 أجزاء من الصخور جزءين من الرمل جزء واحد من الإسمنت نصف جزء ماء
3 parça kaya 2 parça kum tek parça çimento yarım ölçü su
3 parts rock, 2 parts sand, 1 part cement, and half part water. No matter where you are in the world, this is the Universal Concrete Mix Design. As our Universal Mix Design showed, there has always been 4 key ingredients to concrete: rock, sand, cement, and water. We would like to draw an analogy from the 4 main ingredients in our concrete to our concrete conference speakers, audience, advancements, and projects. In our analogy, the projects that we have highlighted at this conference over the last 70 years are the water of the conference. Here are a few of the projects highlighted in previous conferences. Likewise, the rocks of our conference are the speakers that have presented at previous conferences. Here are a few of the previous speakers. You, the audience, are like the sand to the concrete. Many concrete advancements have been covered at the previous conferences. Here are a few of them. Just as mixing the rock, sand, cement, and water results in concrete, the mixing of our 4 ingredients of the conference results in a conference that provides a knowledge distribution path of concrete. Here is a preview of the chapters to come. Chapter 1, History of Minnesota Concrete Conference with Tom Beckin, Robert Randall, and Mac McCullough.
But overall, still, the concrete industry will stay the same. We still need sand, gravel, and cement to make it work. And so we want you to attend the next conference so that you do learn a little bit more about concrete and how it functions. We appreciate your time. Thank you.
Chapter 2, Decade of Strength, recorded at the 50th Annual Concrete Conference with Tom Dykoff. Come back with us to the year 2000 when Tom Dykoff reviews the Decade of Strength. Chapter 3, Time Travel to the 100th Annual Concrete Conference with Nancy Doppenberger, Dave Cassetta, and Kevin McDonald.
And as usual, Vitruvius, we haven't got time for your long-windedness. I'm Kevin McDonald, and I need to talk to myself in the past. Kevin, get over to the microphone.
It's Kevin.
Oh, hello, Nancy. Anyways, Kevin, where are you? Get over. Oh, there you are. Don't believe this. Shut up and listen.
Chapter 4, University of Minnesota Research with Kathy French.
Other things over the years that we've been involved with at the university just nearby, we have 2 large structural engineering labs, the Galambos Lab and the MAST Multi-Axial Sub-Assemblage Testing Lab. With those labs, we've done, structures up to 30 feet tall, large portions of structural walls. Some of my very early research when I finished as a PhD student was looking at the effects of multi-directional loading on components of structures. And, in recent years with our large mass facility, we've been testing up to like a 3rd scale, 6-story wall structure within that building, and trying to make impacts through our research on things like code changes and transferring the research that we do into practice.
Chapter 5, Now and Then with Josh Edwards.
How concrete is actually made. It's one of the few things that you don't learn in college. You might take a semester course on materials. I would think the good majority of the engineers that are going to these seminars have taken a semester in materials, where in that one semester you learn about concrete, steel, everything. But very little of that knowledge translates to how we make concrete every single day.
Chapter 6, Welcome to the NHL with Mark Binsler.
One of the good stories is we were fortunate enough to do the Wild Arena in St. Paul when we built that. And one of the keys I learned from there is make sure you understand your audience when you talk, because we brought in, the NHL always uses the same people to do their hockey rink floors. So they came into town, we talked to them, and I spent a long time trying to convince them how important if we could use non-chloride accelerators to get the set time they were looking for.
Chapter 7, MnDOT Connection with Maria Mastin.
And so what MnDOT did, and Doug Schwartz, the concrete engineer, and Mark Binsler, Dave Rettner, Matt Zeller, and others tried to look at things differently and not focus acceptance on strength. They decided to go a different way and really focus on water cement ratio.
Chapter 8, Outstate Perspective and Uncle Joe with Don Brown and Dan Bruno.
We always pushed for MnDOT contractor design mixes. Well, we bid a job in Sandstone, Minnesota, out of our Hinckley plant, and lo and behold, 2 days before the job's going to start, we were informed that this was contractor mix designs, which we hadn't done any of the testing.
Chapter 9, Kevin McDonald addresses the 100th conference.
Hello, potential visitors to the University of Minnesota's 70th annual conference, but looking forward as well, hopefully, to the 100th annual conference. I'm sure that the robots that will have replaced us in probably 100 years that do a perfect laser deposition of concrete and watch it get 3D printed will greatly enjoy this video.
Chapter 10, Pat Mancini's Plea to Maria.
Hey, my name is Pat Mancini.
And this song is especially written for Maria. Come on.
You have just seen the promos for all 10 chapters. If you would like to watch the full-length version of any chapter, please click the link attached. Chapter 1. History of Minnesota Concrete Conference with Tom Becken, Robert Randall, and Mac McCullough. Introducing Robert Randall.
I'm Bob Randall, and I've retired after 35 years in various positions with the Portland Cement Association, working out of Minneapolis in the north central region. I called representatives of the concrete industry to see if they would be amenable to attending a luncheon to discuss the problems in Minneapolis. And at this luncheon, we had about 20 representatives of the engineers, the contractors, the architects, ready-mix producers, cement suppliers, and others. And it was decided at this meeting that it would be a good thing to have an annual concrete conference. And as a result of this meeting, it was set up for a 2-day concrete conference at the University of Minnesota. This conference was very successful and was attended by 248 engineers, contractors, and others from 6 states and Canada. Then the conferences were scheduled every year in various places. In fact, I think the first 15 or 20 of the conferences were held at the University of Minnesota.
Introducing Tom Becken at the 50th Annual Concrete Conference.
Hello, I'm Tom Becken. I'm with the Simstone Products Company. Our company has been in the ready-mix concrete business since 1941. The company was started by my grandfather and father back in 1927 in the block business. And yes, there has been a lot of changes in the concrete industry in the last years. We have gone from producing ready-mix concrete by pulling levers by hand to where now we use nothing but computers and printout tickets and all automated batch plants. Prior to that, when I first started, all we used was we broke the cement in bags, put it into the ready-mix trucks. We had sand, the sand and gravel was weighed out, and all the levers were pulled by hand. And as the industry has grown, we used to have mixers that hauled 4, 5, and 6 yards, and we had a separate engine drive on the mixer. And today, where most of our trucks are hauling 10-yard loads with the engine being powered off of the truck. The concrete has changed considerably. We used to produce concrete on the basis of 1, 2, 3, or 1, 3, 5, or 1, 3, 4 by proportions. Then I remember it went into where we were producing concrete by the bag, 5 bag, 5.5 bag, 6 bag. And then the industry changed some more, and it changed where we were producing concrete by strength, 3,000 pounds, the 3,500s, the 4,000 pounds. And the most admixtures that we were using was air entrainment, and then we would use calcium chloride in the summer or in the winter and spring and fall. And now the concrete industry has changed where we have gone to using the water cement ratios, and by adding microsilica and super plasticizers and all types of different admixtures. On some of the concrete we produce today, we produce it without very little water, and using a lot more admixture, a lot of admixtures. We used to use nothing but 3/4 and half, and then add the 3/4 inch gravel and 1/2 inch. Then we got away from that and went to making 3/4 and 1/2 inch and 3/8 combined into one. Now we have changed back, and where we are adding the different sizes of gravel and blending them back in to make a better product. We are just building a new plant down in Burnsville, which we're opening, and there we have 10 bins so that we can accommodate all the different aggregates that are being used today to make ready-mix concrete. The sand is about the only thing that has stayed consistent, and I can remember going to these concrete conferences back in the 50s and the 60s. Also, the industry has changed in the fact that there are a lot less producers of ready-mix concrete in the Twin City area. At one time, most of the producers were one plant operators or 2 plants. Today, it's down to 3 or 4 companies, and they have multiple plants rather than each plant being owned by one individual. As I look at it for the next 50 years in the ready-mix industry and the concrete industry, I see that we will be coming up with more admixtures to...
Introducing Tom Beckin now.
Tom Beckin with Simstone. I've been in the industry for over a long time. I don't even want to tell you how long I have been. But I spoke at the conference back in the 50s, early 50s, when the organization was 50 years old. And in what has changed in the last few years, the only thing that really has changed, we still use sand, gravel, and cement, and we still use a lot of admixtures. The only change is the admixtures have changed. Cement has not changed, sand has not changed, gravel has not changed. All we're doing now is putting all this together and hoping everything comes out okay by using all of these concrete admixtures. And as we look to the future, I see that the industry will change somewhat. The loads are bigger than they were then. The way we do it is going to be different, but overall, still, the concrete industry will stay the same. We still need sand, gravel, and cement to make it work. And so we want you to attend next conference so that you do learn a little bit more about concrete and how it functions. We appreciate your time. Thank you.
Introducing Mac McCullough.
Hello, my name is Mac McCullough. I'm a very independent structural engineer, private practice. I've been a member of this committee since 1978. Most of the brochures that you see are the ones that Pack-Rat Me collected and saved. I've attended all of those conferences. This committee has always been composed of industry people, and with just enough university guidance to get us through the red tape of the bureaucracy that we work with. And we're glad to have this 50th anniversary, and we're glad to see all you loyal fans and friends out there. Thank you. Goodbye.
Chapter 2, Decade of Strength, recorded at the 50th Annual Concrete Conference with Tom Dykoff.
Tom Dykoff will be our riverboat captain and guide us back through the 1980s, the Decade of Strength.
As we review the 1980s, prior to the 1980s, 4,000-pound concrete was the norm. concrete was developed as a means of aiding and facilitating early stripping of formwork. And case was the Hubert Humphrey Metrodome. In 1982, 8,000 PSI concrete was introduced. And we'll go to the other side of the river in St. Paul for this. This occurred at the Jackson and Sibley Towers, St. Paul, for the structural members. In 1984, we developed 9,000 pound concrete. That again occurred in St. Paul at the World Trade Center for the superstructure. In 1985, 10,000 pound concrete was introduced, and that occurred on the other side of the river in Minneapolis at the Northwest Tower. The super piers, which were the composite columns for the structure. In 1986, 12,000 pound concrete was introduced. And that occurred at the First Bank building. You can see we had winter construction going on here with the new enclosures. And that 12,000 pound concrete was used for the composite columns for the super piers. That building now is known as the U.S. Bank building. 1989, 14,000 pound concrete was introduced. Again in Minneapolis, that's the building to the right. That's the Dean Bosworth Tower. And 14,000 pound concrete was used again in 1997 at the American Express 707 building. What does it take to compromise or to develop 14,000 pound concrete? The design mix, cementitious materials. First component is type 1 Portland, 850 pounds of materials. Fly ash, add 125 pounds to the mix. Microsilica, an additional 100 pounds to the mix. This gives us a total of 1,075 pounds of cementitious material. Looking at admixtures to develop this mix, we have low-range water reducer, 30 ounces per cubic yard. Retarder, another 30 ounces per cubic yard. And high-range water reducer, 225 ounces per cubic yard. That alone totaled 285 ounces or 4.5 gallons per cubic yard. So again, we have 120 pounds of fine aggregate, now we go to the aggregate side. Fine aggregate, 1,020 pounds. Coarse aggregate, 1,800 pounds. Water, 300 pounds or 35 gallons. Which gives us a water cement ratio of 0.28. You can imagine mixed with a 0.28 water cement ratio, how do we even get that out of the truck? The only way we can accomplish that is with those 4.5 gallons of the admixtures. So again, reviewing that mix, you have cementitious materials over 1,000 pounds. You have the admixtures of 4.5 gallons, and then the aggregates with that water cement ratio of 0.28.
Chapter 3. Time travel to the 100th Annual Concrete Conference with Nancy Doppenberger, Dave Cassetta, and Kevin McDonald.
Hi, I'm Nancy Doppenberger. I'm the Deputy Commissioner and Chief Engineer for the Minnesota Department of Transportation. And I'm here to talk to you today about the 50th Annual Concrete Conference. That was the concrete conference where we did some time travel. We traveled 50 years into the future to talk about the 100th Annual Conference. And Dr. Vitruvius, played by Dave Cassetta, was there to talk with us about concrete in the future. Also, Kevin McDonald made an appearance and he talked with us about concrete.
When we planned on presenting what concrete would be like in 50 years, our lack of completely understanding concrete back here at the turn of the century interfered with our clear vision. So we decided that the only way to really know what concrete would be like at the 100th annual concrete conference would be to go there.
Hello, I'm Dr. Dave Vitruvius, and I would like to welcome you and Nancy and all you folks back at the 50th Concrete Conference to the Dick McNamara Center, where we're about to start the 100th Concrete Conference. So Nancy, how was your trip?
It was timeless.
So are you experiencing a sense of deja vu?
Yes, I am.
Well, so are the rest of us.
Dr. Vitruvius, as you know, our goal here is to have a dialogue back with the folks at the 5th Annual Concrete Conference. At this time, I'd like to direct your attention to the remote camera over in the corner. If any participants would like to ask Dr. Vitruvius a question about concrete in the future, please step up to the microphone. While we're waiting for a question, Dr. Vitruvius, I would like your thoughts on the last 50 concrete conferences.
Well, that's interesting. First, I'd like to thank for all you folks for this film that you made for us. It was very helpful in planning for the 100th Concrete Conference. This film recognizes some very, very interesting leading people in the industry back at the end of this last century. But I must say there was many more that deserve recognition. The people like Frank Marzatelli, people like Irv Dahlstrom, Charles Britzius, and Norm Henning were also responsible for the early concrete conferences. There are also even other people outside the conference who were a very important concrete industry. The batchmen, the truck drivers, the pump operators, the puddlers, and the finishers also were all very important. Guys like a Daryl Stoliker, who the old-timer told me was the person most responsible for designing a very wonderful lightweight concrete, which would be pumped to top of many buildings, even in the winter time. There was an advancement back in the 1980s. Okay. Daryl also designed the first 12 and 14,000 PSI mix design used in the Twin Cities. Hey, you! Where are you going? You sit it down, okay?
Dr. Vitruvius, we have a question. Please state your name followed by your question.
I'm Dan Warbeck, and I'm wondering about the future of aggregates.
Well, Dan, that question is a very interesting answer.
And as usual, Vitruvius, we haven't got time for your long-windedness. I'm Kevin McDonald, and I need to talk to myself in the past. Kevin, get over to the microphone.
It's Kevin.
Oh, hello, Nancy. Anyways, Kevin, where are you? Get over. Oh, there you are.
Don't believe this.
Shut up and listen. We don't have much time. Invest all of your money in it.
Nancy, I'm gonna get you back.
That's right. Richard Staley and John Ravisto are about to go on stage.
Well, John Ravistra, yes, I remember him. I believe his greatest work was in the salt in the pasta water, like the pasta in the pot. But
Dr. Vitruvius, how do I get back?
Nancy, it's just like in the movies.
There's no place like home.
Remember what I told you.
There's no place like home. No place like home.
See, how was your trip? Are you experiencing a sense of deja vu?
Yes, I am.
So are the rest of us.
I brought something back from the future. Dr. Vitruvius wants me to have you folks construct a collective journal. We will circulate this logbook during the remaining morning session. Dr. Vitruvius would like you to enter your thoughts or your signature here today at the 50th Annual Concrete Conference. He will read from the selected entries at the 100th Annual Concrete Conference. The last 10 years have flown by very quickly. Dan, we're getting old. The group of us that conceived this presentation during lunch at the 40th Annual Concrete Conference have hopefully accomplished our goal to entertain you.
At the end of that part of the workshop and video, we had a book for folks to sign, and we appreciate all those who contributed. Now we're going to show you some of the quotes that came from that book about 20 years ago.
I have been coming to the conference since 1975 and every year find it very interesting. The conference reflects the progress in the concrete industry. The most critical ingredient for quality concrete construction is the pride and commitment of all the folks involved to build for a future they may never see. We placed a parking ramp in downtown St. Paul this month with 12,000 psi air-entrained concrete. Will it still be there at the 100th Annual Concrete Conference? The review of the first 50 years of the conference was very well done. The technique and knowledge we have learned will undoubtedly bring better and more durable concrete products and buildings. At the 50th Annual Conference, I am encouraged by the progress we have made in the quality and placeability of concrete. However, we have a long way to go. I would love to be in attendance at the 100th year conference at age 98 to see how far you have come. The industry is great because the people in the industry are great. Problems: shrinking workforce, lack of aggregates. Innovations: fibers, lightweight concrete, new additives, white topping, synthetic bars. Future: synthetic aggregates, increased mechanization. Chapter 4: University of Minnesota Research with Kathy French.
My name is Kathy French, and I'm a faculty member at the University of Minnesota in the Department of Civil, Environmental, and Geoengineering. And I've been a member of the faculty since 1984. And just about from the beginning of my tenure at the University of Minnesota, I've been participating in one way or another with the Concrete Conference. I think back in 1986 might have been my first talk. We used to have a feature at each conference where the U of M would give like a 15-minute update or a little bit longer presentation related to what cutting-edge research we have going on at the university. And so since that time, I think I've been probably a member of the committee since 1987, and then off and on over the years till today in 2020. And over the time, some of the research talks that we've talked about, we've had faculty at the U and collaborators, Carol Shields, Art Schultz, Roberto Leon, talk about some of those features. And when you look at the timeline, kind of back in the beginning, we talked about things like high strength concrete, where that was a very new up and coming thing. We've done work with self-consolidating concrete over the years, and we've also been looking at bringing in speakers that are renowned speakers nationally and sometimes internationally as well. And so, you know, in more recent, I'd say the last decade, one of the key things for the concrete industry and other industries has been the issue of sustainability and resilience. You know, we have limited resources, and I think that the industry is really taking to mind some of the more critical needs to ensure that we have a sustainable product. And so I remember one of the opportunities in serving on the committee is identifying great speakers for each of those topics. So one of those that we brought in is Andrea Schocker, who's now at the University of Minnesota Duluth, and other you know, fantastic speakers who are involved in kind of changing the environment and technology through activities, for example, in the American Concrete Institute. So there's committees associated with sustainability. I've been a member of ACI 318, which is the Structural Concrete Committee, since 1995. And so another thing that we try and do at the conference is to give the community in this area a preview of what some of those up and coming changes are to the structural building code. So they'll be aware of what's coming, that we can answer those questions. And sometimes it's through questions in the audience that can drive input into those committee changes too. If we're working on the committee and making some changes if something seems too complicated or is going to have a large impact on the industry. It's kind of going out to conferences like this where we can get feedback for input on changing the code. Other things over the years that we've been involved with at the university just nearby, we have 2 large structural engineering labs, the Galambos lab and the MAST multi-axial sub-assemblage testing lab. With those labs we've done, structures up to 30 feet tall, large portions of structural walls. Some of my very early research when I finished as a PhD student was looking at the effects of multi-directional loading on components of structures. And in recent years with our large MAST facility, we've been testing up to like a 3rd scale 6-story wall structure within that building and trying to make impacts through our research on things like code changes and transferring the research that we do into practice. A few other things that we've done at the U related to that we've talked about at the conference is a lot of infrastructure related research. Over the years, we've been supported, for example, by agencies like national agencies, federal agencies like the National Science Foundation and the National Cooperative Highway Research Program. And then locally, we've been supported by the Minnesota Department of Transportation. And some of that work has supported projects involved with pre-stressing producers of like bridge girders. So there we've been involved with high strength concrete, self-consolidating concrete, and also we've been involved with field projects. Like we were involved with the instrumentation of the I-35W St. Anthony Falls Bridge, where it was called a smart bridge structure that was instrumented with more than 500 sensors that's been monitored over the last decade. So again, we've been very fortunate to have the relationship with the conference and with local industry in getting the word out on the research that we do, and also in participating with the conference planning committee on ensuring that we can get topics in that are cutting edge and identify some of the speakers who are cutting edge speakers.
Chapter 5, Now and Then with Josh Edwards.
Sure, my name is Josh Edwards. I'm the Vice President at Apple Valley Ready Mix, or AVR. I've been going to the concrete conference for the better part of 20 years. I've been involved in the concrete conference for another dozen, on the planning committee for probably 8 or so. I lose track after a while. It's amazing some of the stuff that I've learned in that concrete conference, and especially in planning it, on how complicated concrete in this market is. I think it's one of the most complicated concrete markets in the country, filled with great speakers like Ken Hover and Brant Mather. It's amazing to me where we've been and where we go to. Speaking of where we go to, we just made our first concrete last week with 14 constituent materials in it. And I only know that because the computer shut down when it tried to make a concrete with 14 constituents in it. So that just gives you an idea of how complicated things can get. When I started at AVR, we had probably 200 different mix designs. Now we have well over 2,000. And I think we had, roughly 8 different admixtures, and we just recently plumbed one of our plants for its 22nd admixture. So incredibly complicated. I've learned a tremendous amount through the years from people that are also on this list behind me, like Kevin McDonald, about how complicated concrete can get, but yet you still need to have it workable. I spend a lot of my time at AVR teaching, going into engineering companies and going into flatwork finishing companies, the self-performing GCs, and telling them about how concrete is actually made. It's one of the few things that you don't learn in college. you might take a semester course on materials. I would think the good majority of the engineers that are going to these seminars have taken a semester in materials, where in that one semester you learn about concrete, steel, everything. But very little of that knowledge translates to how we make concrete every single day. So I'm constantly going in and teaching engineers about the importance of specifying a water cement ratio, specifying low cementitious material contents, and what that really means for the people that actually have to finish that concrete, and vice versa. Talking to contractors about the importance of water cement ratio and how adding water on site is a negative in almost all situations. So hopefully a lot of that is learned through the concrete conference. I know I learned a lot of that by going to the concrete conference, and we hope that in the future we start to get into the areas of where we're going to in this conference with specifying for modulus. That is one of the first things that's been specified in town here. We're going to have a presentation on it this year on what does the modulus of concrete even mean, how to test for it, what are some of the drawbacks or some of the pitfalls for testing for modulus. I think we have a presentation on supplementary cementitious materials. We're currently running out of supplementary cementitious materials in this market, so what does the future hold with natural pozzolans, and looking at other pozzolans that may be used, ground glass, maybe benefiting natural pozzolans to be used. What are we going to do if we do indeed run out of fly ash? Some of the biggest changes, or some of the things that we really work on a lot now, are mass concrete. Mass concrete's come a long way. Again, a lot to thanks Kevin McDonald. We're doing a lot with high strength, 10,000 psi, 12,000, 14,000 psi concrete. A lot of real high durability, really low water cement ratio concrete. We're working a lot with a lot of really high flow concrete. Seems like we're getting a lot more steel in these structures, and we need to be able to get concrete that's workable enough to work its way in and around all these steels. It wasn't but 5-6 years ago you very rarely heard of self-consolidating concrete. Now we make it almost every day. Some of the things I'm really looking forward to in the industry is in-transit measurement of concrete, so monitoring the air content and the slump of the concrete in transit, and be able to adjust that air content and slump in transit. I think you'll start to see a lot of work with regards to that in the future. I know we're looking at a couple systems right now where we can monitor the air content before we even deliver it.
Chapter 6. Welcome to the NHL with Mark Binsler.
Hi, I'm Mark Binsler with Aggregate Industries. I've been in this industry for 25, 30 years now, and been involved in, I've started going to the U of M Concrete Conference right when I started working for MnDOT, which was in 1985. So I've been to a whole bunch of them and never missed one. One of the good stories is we were fortunate enough to do the Wild Arena in St. Paul when we built that. And one of the keys I learned from there is make sure you understand your audience when you talk, because we brought in, the NHL always uses the same people to do their hockey rink floors. So they came into town, we talked to them, and I spent a long time trying to convince them how important if we could use non-chloride accelerators to get the set time they were looking for. The Canadian gentleman looked at me and said, all we do is turn the temperature up through the pipes that are in the floor, so we control it all ourselves. So I didn't know what I was talking about and learned that the hard way. I guess one of the big jobs we had, we were able to supply the concrete to make the segments for the St. Croix Crossing Bridge. We had quite a great situation there. Our Nelson aggregate plant is on the Mississippi River. So we convinced the contractor to set up a casting yard. They were able to make those huge segments. We loaded them onto barges. They barged down the Mississippi to Prescott, turned north and went up to St. Croix, and then they took the segments right off. right underneath the bridge and lifted them right on into place. So that was really a great project. The Lafayette Bridge was really our first river bridge for aggregate industries, and it was right at the time where mass concrete was becoming a bigger issue. Before that, we did some very big structures that for MnDOT that there was no mass concrete done to it. But at that point, the Lafayette Bridge, it's a big steel structure. It had a lot of big mass foundations under it. So we did have our first foray into mass concrete. It was a very interesting work. We learned about modeling, we learned about temperature rise, we learned about differential and all those things. It's kind of a commonplace thing we do now is mass concrete. Almost every bridge has some mass concrete, but at that time it was kind of unique. One of the issues that people have talked about a little bit is white topping. I was involved when I worked for MnDOT way back in the old days. The first job, there was a test section done on Highway 30 down in southern Minnesota. That was a hugely successful project. The concrete section lasted many more times than the asphalt section did. I know we've done some at Min Road. I think there's a lot of future in white topping, and I'd like to see more of that done.
Chapter 7, MnDOT Connection with Maria Mastin.
Hi, my name is Maria Mastin, and I'm the MnDOT concrete engineer. I started back at MnDOT in 1995 as a student worker on the Office of Materials and Road Research, working at Min Road. And I transitioned into pavement management and then into my future career in the MnDOT Concrete Engineering Unit. Worked my way up from assistant concrete engineer all the way up to currently being concrete engineer. I'm going to talk about the MnDOT water cement ratio specifications. Our concrete pavements were failing prematurely in the late 80s and early 90s, and a lot of those were material issues. And so what MnDOT did, and Doug Schwartz, the concrete engineer, and Mark Binsler, Dave Rettner, Matt Zeller, and others tried to look at things differently and not focus acceptance on strength. They decided to go a different way and really focus on water cement ratio. And from that, we've now, since 1997, we've had an implementation where strength is not a specification, and everything is based on the water cement ratio. And surprisingly or not, we cook concrete in the field at the plant and cook all the water out to see how much water is actually in the concrete, and we use that as a verification of the water cement ratio on our concrete paving projects. That, like many other projects, could not be done without cooperation and collaboration between the industry and the agencies. So MnDOT had to learn to see what risks there might be and accept that, you know, everything isn't going to be perfect as we learned and worked through all of this. But I truly believe, and I tell people, that we've got some of the best concrete pavements in the country because we look at things from a durability standpoint and not a strength standpoint. All right, looking back in time, in 2011, I was part of a presentation given at the concrete conference on the MnDOT Transit Delivery Time Study. That was a great opportunity for MnDOT to partner with the industry. And what we did was, the industry said, you know, we just can't deliver concrete within 60 minutes with traffic and everything else. And so can we go out to 90 minutes? And what we did was we sat down with industry and then worked together with industry and worked at several ready mix plants throughout the state, and we checked what we could do. We were focused on the durability of the concrete and seeing if we could still deliver it in 90 minutes. And what we found was that, yes, we can deliver it in 90 minutes. Our goal is to always add all the materials at the plant. We see that the materials all get mixed in the best and the admixtures and everything, and that was in partnership with some of our very own members that are very involved in the concrete conference, including Dan Bruno and Daryl Stoliker and our ready mix producers. And so MnDOT has seen benefits from that to date, and most of our concrete can easily be delivered within the 90 minutes. I'd like to talk a little bit about Minroad today and what's changed with Minroad. So Minroad was built in 1992 as a cold weather pavement test track, and it was funded by MnDOT. What's changed over time, though, is that there has been great interest by many other universities, industry, academia. The National Road Research Alliance has been formed, and that's a pooled fund project that entails multiple states. And what it has done is it's allowed Minroad to become much more of a national research cold test track facility versus just a local Minnesota project. And what we've been able to do with that is we've been able to try new and more different interesting things that interest many people beyond Minnesota. And a couple of the things that really are starting to advance concrete that we've tried at Minroad are use of fibers. We've had the ability, what Minroad does for us is it lets us try things that we're not quite ready to try on our own highways or bridges or structures, any of those other sorts of things. But Minroad lets us dare to fail. And so a couple of the things that we've tried more recently is we've incorporated fiber reinforcement into our concrete pavements out at Minroad, all the way down to trying 3 and 4 inch thick concrete with fiber reinforcement on the interstate and on the low volume road. Another thing that we're fortunate to be able to do is industry is always saying, well, when can we load the pavement, when can we load the bridges? And so we actually poured some concrete a few years ago now, where we took and loaded concrete that was 2 and 3 hours old with a half-ton pickup truck. And so they slowly drove onto it and drove off of it, and they did that, cycled back and forth. And what we found was 2-hour-old concrete didn't even make a dent into the concrete. So there are things that we're learning at Minroad that, like I said, we can dare to try there and can't try other places. Contractor mix designs and MnDOT. MnDOT for 60, 70 years designed our own concrete mix designs, and what changed over time was MnDOT's mixes were very basic: cement, not even fly ash, rock, sand, and water. And that's what we did, and we did it for 50 or 60 years. And over time, other materials came into the market, and fly ashes and admixtures. Admixtures changed so much, and it is so hard to keep up with. But even back to our water cement mixes and paving. Paving in the mid-90s is when we first started to go to the contractor mix designs. And with that, we didn't even use water reducers. And so that was really MnDOT's first big step into even allowing admixtures on our projects. Besides air and training admixtures, we've put those in for many, many years for freeze-thaw durability. But just dabbling our toes into the water cement ratio specifications and use of water reducers. And we've since evolved. We have a high performance bridge deck specification that requires performance testing. That was a definite change for the industry, where they were used to MnDOT giving them a cookbook recipe, and we turned and said that, you know what, you guys know your materials, you know your mixes, you put the mix together, batch it, give us the test data, and we'll evaluate it, and if it's good, it'll be good for 5 years. So that works really well when you're going to use a project, when you're going to use that mix design on many projects. It gets to be more challenging for our outstate producers who maybe have one bridge project every 5 years, and so they've got a big investment to make, and that's something that needs to be considered from the agency side and the industry side as to whether or not that investment is worth it. But it definitely brings a challenge to have contractor mix designs and required preliminary testing in the outstate area, and it does affect the metro area too. So that definitely makes things interesting. But from there, we even went further, and in 2016, MnDOT implemented contractor mix designs for all of our concrete mixes. And so every mix design that a producer provides now, they have to give us the recipe, and we'll review and approve it for mix designs that can be used on multiple different projects. And with contractor mix designs, we eliminated the minimum cement content, cementitious content requirement, and we really opened up the use of admixtures because the contract producers know their materials, and so they can use virtually any admixtures except accelerating admixtures on most any mixes. And so those are really big changes just with the technology and everything that's improved with the industry.
Chapter 8, Outstate Perspective and Uncle Joe with Don Brown and Dan Bruno.
My name is Don Brown. I've been in the ready mix industry since 1978, starting out with E.F. Hall's Sons Incorporated, which then got purchased by Bowerly Brothers, which then got purchased by Knife River. So I like to say that I've worked for 3 different companies, but my desk never changed. And then later on, and now presently working for Kohner Materials, which was his company in southeast Minnesota, Modern Ready Mix, Wabasha Ready Mix, and some Wisconsin companies too. I'd like to start about talking about the contractor mix design, as I was on the board of directors at a young age for Aggregate Ready Mix Association. We always pushed for MnDOT contractor design mixes. Well, we bid a job in Sandstone, Minnesota, out of our Hinckley plant, and lo and behold, 2 days before the job's going to start, we were informed that this was contractor mix designs, which we hadn't done any of the testing. So then we made some phone calls to MnDOT and basically led up to the curb contractor. You can use their mix, but if it doesn't pass, the curb will come out. So we felt we had a good mix design and went through with it, and everything came out okay. Long story short, from now on we checked the special provisions for being in the outstate in the days for the contractor mix design. And it was kind of interesting. Everybody at MnDOT worked very well with us to get this going, because I believe it was the first outstate contractor mix design for a MnDOT project. And being that outstate doesn't do as many MnDOT jobs as in the metro area, they were a little more forgiving with getting things done, but we had to do it. So it was a success. And that is part of my 40-year history in this business, along with thanking a lot of peers in this industry to work hand in hand with to make sure concrete that we produced was very durable and met all the specifications. Which leads me to the Winona Bridge project we did, which was basically all contractor mix designs. We worked very hand in hand with Danny Bruno at AET. He helped us immensely. We had to meet the specifications for 160 degree or less curing temperatures, which we did a lot of pre-testing for this mix. It was a big project for outstate Minnesota, and it was a great success with Ames Construction and David Duke as the project engineer and project manager, along with Jerry Voles at Ames. So I learned a lot in the outstate industry, again leaning on a lot of the peers in this industry to learn as we go to build such a big structure in the outstate Minnesota. Again, everything was great. We did a rehab on the other bridge and worked with some other mixes. We looked at a lightweight bridge deck, which they decided not to use, did a bunch of testing, but hopefully that led to some of this internal curing that we've been involved with as well. I just recently finished one. So in the 40 years of my experience in the ready mix, there's been a lot of changes, but as long as you communicate, go to seminars, talk to people that have been around even longer than you, things will go well, as long as you do follow all the procedures. And congratulations to the University of Minnesota Concrete Conference for their 70th year. Thank you.
Hello, this chapter is about the workers, probably the most important people involved in the whole concrete industry. We're talking about the ready mix drivers, the puddlers, the screeders, the finishers. Those are the people that actually do the craftsmanship. They're the people that actually end up making the final product what it is. I'd like to talk about Uncle Joel. He represents a lot of the workers. And in 2013, when the ACI International Convention was in Minneapolis, Uncle Joel got a Lifetime Achievement Award, where he had to go up in front of a whole bunch of suits and ties and receive an award. And when he was up there, the moderator off the cuff said, "Anybody got any questions for Joe?" And someone asked a question, and the question was, what's the difference, Joe, between finishing concrete in the 1950s and finishing concrete now? Back then it was year 2013. And Uncle Joe gave an elegant answer. He said, the biggest difference is there's so much more surface area finishers are responsible for due to pumps, conveyor belts, a lot more concrete's put down, a lot more surface area finisher in the finishing tools. And then he looked at his plaque, he looked up at me and he says, "Come on, Danny, let's go back to St. Paul." And he walked out of that place to a standing ovation of all the suits and ties.
Chapter 9. Kevin McDonald addresses the 100th conference.
Hello, potential visitors to the University of Minnesota's 70th annual conference, but looking forward as well, hopefully, to the 100th annual conference. I'm sure that the robots that will have replaced us by 100 years that do a perfect laser deposition of concrete and watch it get 3D printed will greatly enjoy this video. But my name's Kevin McDonald. I have a relatively odd education, a bachelor's degree in chemical engineering, and then graduate work including a doctorate in engineering materials, which was at the time when I did it in the mechanical engineering at the University of Windsor. And you might wonder, why is a person who studied chemical engineering and who has studied mechanical engineering talking to you today about concrete? And the reason is that concrete is a fascinating material, and my exposure to the deteriorating and decaying infrastructure we find ourselves with here in the first quarter of the 21st century, and certainly the last half of the 20th century, is due to corrosion of reinforcing steel. And that corrosion of reinforcing steel was not something that was predicted, but something that we encountered so frequently how things work in engineering. And concrete is a great material. Put steel into the concrete and it will passivate, it stops corroding, and it does some wonderful things. If we keep it away from salt and keep it away from carbon dioxide, then we end up with a great material that will last forever. Unfortunately, the roads in this area, I'm sure now the global warming has caused it not to be the case, but here in 2020 we still put salt on the road to melt the ice that occurs, and that salt goes into the environment, and a lot of it runs off and goes into aquifers, but some of it penetrates into the concrete. If it reaches the level of the embedded reinforcing steel and the concentration is high enough, it depassivates the steel and it starts to corrode. As a teenager, I got a job with an engineering firm doing inspection, detailed condition surveys on bridges in Ontario. And those detailed condition surveys were required because the structures were deteriorating due to corrosion of embedded reinforcing steel. And so an engineering job when you're still an engineering student is a great experience, and I began to ask lots and lots of questions. And among those questions were, why don't we just stop the chloride ions from moving? Why can't we? This is obviously a diffusion and a mass transport problem. Why can't we just stop them from moving? And of course the reason is that the structures were designed to resist the strength of the concrete, the structures were designed to have strength, to resist the bending forces, to resist the imposed loads, to resist the environmental exposure, but not to resist the penetration of water, or worse, the movement of chloride ions in that water by concentration gradient. And so my great interest, sparked in a 19-year-old kid, was how can we design our concrete mixtures to prevent, to the extent possible, the corrosion of the embedded reinforcing steel in the useful lifetime of the structure. Now, we've tried a number of cases, a number of opportunities, and at the time that I went to graduate school, I was advised by a colleague of mine, why would you bother studying the corrosion of reinforcing steel and concrete? Because we are going to paint everything with epoxy coating, and that'll be wonderful. Of course, as so many other things, it appears that putting a rigid non-ductile coating on a ductile material and then subjecting it to normal construction practices, which include leaving the steel in the sun, dropping steel tools on it, dropping the bars in bundles, had a tendency to partially crack, and subsequent investigation over 20 odd years indicated that these bars were not being protected by the epoxy, which seems to last about as long as it takes for the chlorides to get down to cause corrosion. And so we persevere, and we continue to make concretes that are designed not just for the structural purpose, which of course is important, but for their durability, for their resistance. Here in 2020, all the cool kids are trying to make structures that last for 75 to 150 years, depending on who you are, and we all solve a bunch of differential equations. Some of those differential equations are still solved with an assumption that the concrete doesn't crack, which is a poor assumption. I mean, they're also solved assuming that the concrete has certain properties that may or may not continue to change over time. So we're at the leading edge of that development, which I'm sure, because why wouldn't it be, has been solved here in the 100th anniversary of this conference. However, let's talk about some of the things that we have been able to do. In order to deal with the transmission of chlorides, either by transport or rather by flux flowing transport or by diffusion, we've had to make the concrete as dense as possible. And in order to make it as dense as possible, we have to find other cementing materials different from Portland cement that will give us a binder capacity that allows us to restrict the pore structure, to prevent spaces that would be filled with water or would be filled with air and water intermittently from allowing that chloride in. And simultaneously, we have had issues with the temperatures that are developed in large members, in mass concrete. So we look at both of those things together, and while trying to solve a problem on the Lakota Bridge, the icebreaker that was, I'm sure you don't use feet anymore, so it was 4 meters by 4 meters by 4 meters. That's 12 feet for those playing at home. And those icebreakers generated so much heat that they would alter the quality of the concrete. And so we looked at it and developed a series of mixtures to attempt to place these large blocks of concrete without any cooling tubes in the heat of Minnesota. Now, many people, of course, think that Minnesota is many people may think that Minnesota is a cold place, but as you can see today, with the sun beating down, it's going to be almost 30 degrees centigrade or 100 degrees Fahrenheit. So, and relative humidity is same units metric, is it's about 80%. And so we do have some hot weather problems. We're doing combinations of ground granulated blast furnace slag, which you probably still have because we're starting making steel, and then a combustion product from the burning of coal, which you probably don't have anymore. And that material is also siliceous, so you end up with a pozzolanic material. Slags are latently hydraulic, and putting them together with cement, we get a series of reactions that are different from just the cement reaction. We get a much greater refinement. And while we were playing around and trying to optimize these mixes, we started using ternary blends, fly ash and slag in combination with the cement. Fly ash because eventually we would run out of calcium hydroxide, so we wouldn't run in a very efficient pozzolan reaction, but it would, by that time we would get it warm enough so that we would get it warm enough so that we would be able to activate the slag, its latent hydraulicness, or its latent hydraulic properties, by heating and getting that cementing going forward. And we found something that was very strange. Like a lot of scientific discoveries and engineering discoveries, we didn't say like, yeah, what we thought was going to happen worked. We said, that's weird. It shouldn't be doing that. We had replacement levels at about 85%, less than 75 pounds of Portland cement per cubic yard. Strengths around 10,000 psi. It was about 70 megapascals. It was quite a feat, and we were confused as to how that happened. And now the difference between science and engineering, of course, is that engineers know what things cost. And my colleague Dick Staley, about 150 feet from where I sit right now, or 50 meters, was saying that he wanted to build a bunker for his radiation gauges. And he wanted to build it as cheaply as possible. So he suggested that we would get a deal. I would provide him some concrete that met this very strange requirement of having almost no Portland cement. And in fact, we would use recycled aggregate, which started as coarse aggregate and then in addition to fine, and we were kind of egging each other on as to who would blink first as to how much non-virgin material we would use. Eventually we got down to a point where we had about 80 pounds of Portland cement, the remainder of that mixture being recycled material, slag, fly ash, recycled aggregates. And in exchange for the largesse of providing this steady concrete, Mr. Staley said he would run a bunch of testing. And among those, rapid chloride permeability and shrinkage, which we had not looked at before because we were, to be frank, looking at mass concrete and temperature. When the results came back, Dick and I had to have a phone conference because he didn't believe them and neither did I, but we repeated it. We found these materials were very dense, which is probably why they were very strong, but also that they were very resistant to cracking and resistant to the movement of chloride ion. In the long run, American Engineering and I and Semstone and unfortunately at that time the late Dick Staley were awarded the Pankow Award from the American Society of Civil Engineers for innovation for our mixture that only used 2% by mass of non-recycled material. These materials were not just laboratory studies. They started as large pours. And they always say that luck is when opportunity meets preparedness. Unfortunately, we had a steel structure collapse in 2007 and during rush hour in the bridge over the Mississippi River that had to be replaced. Thankfully, there was very little loss of life, but the structure was very important and had to be replaced almost immediately. And we were given the opportunity to design those concrete mixtures for a structure with a 100-year design life. That was about, as we sit here now, about 12 years ago. The structure contains a lot of concretes that have almost no Portland cement in them. Very dense, very low permeability mixtures that readily allowed us to make the large members that were required and deal with their temperature, but also to make them very durable with respect to embedded reinforcing steel and its corrosion. That structure, as we sit here, has used 12% of its useful life. It is well behind where we even predicted it to be in terms of chloride ion penetration. So I'm sure that you are now looking at that structure, which should be about 45 years old now or thereabouts, and I'm sure that it's still in great shape. It has a really cool set of self-cleaning concrete that will use the sun to clean up the air around it. It has all kinds of innovative things. And the reason that we were able to do that is because we had this problem to solve, the temperature. We had this problem to solve. We needed to build a radiation shielding structure, or AET did. And Dick and I had sat in his club, not that far from here as well, and said, you know, I dare you to do this. And I said, well, that's nothing. I'll do not only will I do the coarse aggregate, I'll do the fine aggregate. Lo and behold, we have a material that has been used in the in the heat of the summer to resist temperature. We've also used it, and the I-35W bridge was reconstruction was done over the winter. The crews brought in from California were some of the saddest people I'd ever seen. Expecting in January to be in California, expecting in January to be in California with temperatures of 70, maybe 65 degrees when it's cloudy, and not realizing that it was possible to see minus 40 degrees Fahrenheit on the thermometer, let alone the wind. So we have subsequently used that mixture in lots of places, in award-winning projects, in Brattleboro, Vermont, where we won the 2012 Project of the Year for the Slag Cement Association, on the St. Croix crossing, which was designed to have 8,000 psi mass concrete post-tension tendons, which use quaternary blends, adding a little bit of silica fume for that final boost. And we think of these concretes as though they're multi-stage rockets. We use each of these materials to raise the temperature to get the other materials to go forward. In a lot of cases, the development of these mixtures happens exactly the way that I've described. It's not a bunch of people sitting around in white lab coats who sit down and say, you know, if we just put in a little bit more salt and a little bit less mustard, this would make a great hot dog cover. What it is trying to solve real-world engineering problems, and practical people like Mr. Staley, like myself, like Tom Becken, who you've probably heard from in this as well. Tom Becken owned the concrete company that I worked for. Tom had no idea that we were up to this sort of thing, but he was okay with it so long as we were making money at the end of the day, and we were. So we've gone on to develop these concrete mixtures despite some of the resistance we still encounter here in 2020, which is I don't want any pozzolans, I want straight cement mixtures. It's a very old way of doing things. The problem that we have is so frequently our researchers are doing work using the white lab coats and not paying attention to a real problem that you encounter, which is you actually have to make the material and have labor place it. And if the labor can't place it, it doesn't matter how great a mixture you've come up with. And again, being a strange person, an odd place for someone with a doctoral degree to find themselves, but I ran the quality control department, among other things, of a large ready-mix producer for 10 years. And if the concrete wasn't finished, it couldn't be placed, it couldn't be vibrated, it wouldn't pump properly, then I was the guy who came out, and unfortunately, it was our pumps and our trucks and our mixtures, so I couldn't find anyone else to blame. So I had to sort out and find out what the problem was. We've continued on with that infrastructure construction and trying to build the world that you probably now occupy in the 100th anniversary, where the structures are permanent and they never need to be repaired, because that's what the future always looks like, right? It's if we think back in the 1960s of what the year 2000 was going to be, we were going to be running concrete trucks on the moon. In actual fact, we're still not running concrete trucks on the moon. We're getting closer though. We're going to go to Mars, right? Just skip the moon altogether. NASA's had a very interesting study very recently. But it's that understanding that we need in engineering that we miss sometimes if we look just at the science or just at the practical matters. We need to look at between them. An understanding of how things are executed in the field and an understanding of what could be going on at the molecular level, and combine those together, and that's where we make progress. There's other things that unfortunately have occurred, and people become smarter most of the time, as they age. The great tragedy of the human condition is that the older you get, the more likely it is that your time will run out. Dick Staley, who is a great influencer of some of these projects, passed away very prematurely, and was very much had a very large role in the inspirational use of these materials in infrastructure. We'd already been using them, of course, in mass concrete infrastructure, but it's their durability that lasts for a long time.
Chapter 10. Pat Mancini sings the Oven Dry Blues. Here is a typical MnDOT concrete mix design where the aggregate weights are at oven dry, but the water weight is as though the aggregates are at saturated surface dry. The water cement ratio should be determined when the aggregate is at saturated surface dry condition. This makes our MnDOT mix designs incorrect. Assuming our aggregate has an absorption of 1%, the rock would absorb 18 pounds of water and the sand would absorb 13 pounds of water in order for the aggregate to achieve saturated surface dry from the oven dry condition. This would result in our MnDOT mix design to have a water cement ratio of 0.44. Now sit back, relax, and enjoy Pat Mancini's plea to Maria Maston, our MnDOT concrete engineer, to change oven dry to saturated surface dry.
Hey, my name is Pat Mancini, and this song is especially written for Maria. Come on. Well, Maria, hear my plea. Change oven dry to SSD, cruising by the way, could have been no moisture, it's just the amen, left here oven dry, so it seems, I gotta change for ice cream, make it alright, say goodbye, oven dry, make it alright. Saying goodbye, oven dry. Don't get caught up what I say. Donnie Brown thinks oven dry's okay. Even now I sit and wonder why. How we got started with this oven dry, hey, that was then. Now it's time, changing SSD, make things fine, make it all night. Saying goodbye to oven dry, make it all right. Yeah, we're saying goodbye to oven dry, make it alright, make it all night, make it alright, make it all night. SSD all night. No more oven dry.
Beautiful, Pele.
I don't care what Danny says. Oven dry is okay.